And so you just concatenate it all together, and that gives us the prior distribution in Z, fitting it back to the notation we had in the first hour. And the transition kernel in this particular case is Gaussian, and it's centered about the output of your model. All right, so given this, the probability of jumping to X is this quantity. Right, so this is actually the weak form. This leads to the weak form of 4D-var. Right? Because otherwise, if it's a strong form, then this would become a Dirac delta. So it has no noise, and this is basically, you just take that value you get out here. So you make this 0. So Q goes to 0, so this has to go, this is just the value of, so this is a strong form of 4D-var. Now, if you think of the continuous time version, you think of this as really being a discretization of a process. So you have here the right-hand side of your ODE system. You time step it forward by the Euler method plus adding noise, where the noise, again, has the delta t in it from the Brownian motion. But otherwise, it's exactly like what we had before. So you can write down a transition kernel, which now has 1 over delta t here. And the Q here, and the M is being replaced by this here. Same thing. Nothing changes. Except now you can talk about going to the limit. You can make delta t smaller and smaller, and then this becomes, of course, this formally, without going through the details, this whole chain here becomes longer and longer because n keeps going up, and this delta t becomes smaller and smaller. So eventually you talk about measures over continuous functions, and so then you need measures again. But don't worry, I mean, just keep it discrete and work with it happily. But again, if you do think, you should at least have in mind that there is something in the limit that is a bit nasty, right? And it can have consequences for what you do. Right? But otherwise, I'm a numerical analysis person. I always discretize first and think what are the consequences, and then think about what is the limit and what is coming of it. If you're a probabilist, you would right away start with this and say continuous functions. I define a measure on it, et cetera, et cetera. Now, it has a consequence. So this, as I said, has now, if I give you an SDE, and I take another SDE, the same drift, but I change this. I change this to another constant. That's maybe not even a matrix, just like a number here. So this is, let's make this a sigma here, and this a sigma dash. And let's look at this in the interval 0 to 1. And we can even further simplify it and say we make the drift 0. And then let's just look at these two processes. Brownian motion on its own. So this will be a random walk, this will be a random walk. But let's remind us what we did at the very beginning today. Because this is, we discretized this. So this is you can think of this as a huge, very long vector which we went to the limit. So this very long vector. Each of the increments is Gaussian distributed. So each of these components is Gaussian distributed. Now we had this before, right? And we talked about the length of such an object. Now, this thing on its own, it turns out if this interval is 0 to 1, the length is 1. So all these realizations, the Euclidean distance squared of this object, all the paths have length 1. They can go all over the place, but they have length 1. in a way, in this space of increments measured in this increment space. And so it sits on this radius 1, and then you multiply it by sigma. So it sits actually on the radius sigma. Now you change to a different model with sigma dash. That's a different circle. And so it's mutually singular. These two measures are mutually singular. So basically, the prior generated by an SDE with one diffusion constant is mutually singular to a measure generated by another diffusion constant. Right? So you cannot convert one into another. I mean, there's no radon-Nicodim derivative. Of course, we had some discussion here in the break. It's not the end of the world. It just means that there's a bias. Right? So if you choose the wrong diffusion constant in your estimates, there is a bias. If the truth has, I mean, the idealized world, let's say the real world has a certain diffusion constant there. Of course, we know it's all an approximation anyway. So that's why as a practitioner, you maybe not worry so much about it because, well, the diffusion process is an approximation to begin with. So, but and again, it's just something to have in mind, right? Right? So it introduces a bias in your estimates. So there's a singularity of measures. Now it turns out if you keep this the same and you change this here, you change the drift, that's fine. You can change the drift. That doesn't change. I mean, they have a radon-Nicodim derivative. Right? So you can change the drift, but you can't change the diffusion without going singular. Now this also has good news, because it also implies, and I'm not going to go into the details, that it's actually very easy to estimate these quantities. Because you basically just have to measure the length of your trajectory over a certain interval. And that's a good estimate. I mean, the variance of it. So it's bad news and good news. So it's one thing, the singularity means it's very easy to estimate from finite data. The bad news is it's sort of, if you get it wrong, it has sort of implications. But, you know, for practitioners, it's probably not the end of the world. But just something to know. OK, so this is the underlying process. Now, the observation models, this is your standard forward model. H is a forward operator, the current state, the data at the current state, plus measurement error Gaussian. The likelihood is written down there. So, but there's also something I start liking as a mathematician, because there's a continuous time version of it where you sort of, your observation is like a whole trajectory. It's like very high frequency data. And that's, as we saw in your talk, you're getting this almost now, right? So you get very high frequency data, almost continuous in time. And you might also, another application I'm actually thinking about is when you have a high resolution model that generates output, and you want to use this to calibrate a lower resolution model, parameterizations of a lower resolution model. So your high resolution model gives you continuous output. Of course, you have to build a measure. I mean, you have to build a model, an error model, because there's the representativeness issue. So there is an error. But basically, the data from this high resolution simulation arrives continuously in time. And you can, of course, do subsampling and things like this. But you can also take it as it is and think of it as data you observed. And the likelihood can be written down. And there's no sum now. There are integrals. But again, just discretize the whole thing. Go through the algebra, and you see exactly this integral appearing. It's just Riemannian stuff, essentially, mostly. You have to be a bit careful in the Taylor expansions that you keep all the terms that you need. Because the nasty thing about stochastic calculus, you have terms like delta t square appearing in the Taylor expansions. And you have to be careful to keep all these terms to the end. And you're not just cutting it off at the wrong point. So you have to go, often you have to do in the Taylor expansion one order more. That's it. Right, and then you do base formula. In the discrete case, likelihood time prior, everything is finite dimensional, you're happy. If you're in the SDE case, you work in the space of functions, and so you need this Radon-Nikodym differential. Again, just think discrete, fine. And then the likelihood is the one I just wrote down. Also, this in principle you can discretize, using a quadrature formula. Okay. Right. So, how are we doing time-wise? Is 15 more minutes? Yeah, or 20 minutes? Okay, good. So now, so I basically talked about the big monstrous problem you do in 4D var, right? You have, let's say, you have all the data. Because 4D var you do also sequentially. Just look at one single window, and you have all these variables stacked on top of each other, and you do either the minimization, but I basically now talked about the distributions that come with it as well. But in practice, of course, we often interest only in the sliced distributions at times. And they come in different versions. And the filtering problem is one particular one. So smoothing, for example, says, and I just want to fix the notation here, that at a particular time t, or a discrete index n, I want to know the distribution of the variable at that time, given all the data up to capital T. So the window is 0 to capital T. And then in between, I want to know the distribution, but I want to take into account the whole set of data. So this is smoothing, or I don't know if reanalysis is the right word, but reanalysis is also the same spirit, maybe, that you take all the data you have in a way, but you might still do it sequentially. But anyway, so this is the notation. So the distribution, or the variable at time t given all the data, and that's the distribution. And in discrete time, it's the same. So this is time lower n, and this is t. So filtering, on the contrary, sort of just takes the data all the way up to that particular time. So then the capital T becomes the lower t. So they all equal, right? So both indices are the same. Again, the first index is the time the state variable lives in, and this is the time the observations live in, and the interval that comes with it. It's not just the observation at t, but all the previous data. And prediction is when this is smaller than this. So you advance into the future, taking all the data up to time tau. And these are the distributions we really want to compute often. And so what I'm going to do the rest now, or some of it at least, is to show you that there's a lot of beauty, I feel, at least, in directly computing these things without going through the whole monstrous computation of the whole distribution involving all the correlations as well of all these variables at different times, etc. Just looking at these quantities at these slices. That's now really using the structure of the problem. Of course, the filtering is one thing. So, but before I do this, I see I want to show you another thing which is related to physics. So I mentioned that if this is the same, I can change the drift. And it's still, the measures are sort of compatible. So there's a Radon-Nikodym derivative, right? And the way I'm going to do this change is I replace this noise by the original noise plus a deterministic drift term. So I put it behind the Q, but that's for technical reason I put it there. But basically, this is something deterministic, so it can be added to this. And it also depends on x potentially, and depends on time. So basically, if you multiply it in, it gives you an additional term, q square root of q times u to the drift term. And there's a and now we want to compare the measure if you don't do the correction and you do such a correction. And there's a likelihood. So the two measures, and the likelihood is given by this expression down here. Mentally, you can think of it, you compute solutions, let's say, from this SDE, and then you can reweight them, and then they give you a solution of this. They give you the right distribution, and vice versa. So it's a reweighting exercise. So this is like a data likelihood, but it's a different kind of likelihood. It comes from a change in the equations.